Hi, welcome to lesson 28. So we're going to talk about two sample T procedures. So this is going to be the scenario where we have two populations or groups and we're interested in comparing means between the two independent groups. So we're going to look at side-by-side box plots. We're going to look at the T procedures that we'll use. So we'll specifically look at building a confidence interval for the difference in means, as well as a hypothesis test for that difference in means. And then we'll have a caution there about the pooled T procedures. So here, the example that we're going to use throughout this lesson, we're looking, there's a business manager and they really want to know which server they should be using. Server A supposedly is faster than server B. However, it's going to be more expensive to have an account with server A. So they want to compare the speeds of the two servers to see, is it worth it? Is it worth the extra cost? Should they go with server A or should they stick with server B? So we have our side-by-side box plot here. So here's server A, here's server B. In general, if you don't tell R to do otherwise, it's going to put them in alphabetical order. So looking at these box plots, things we want to consider, we want to definitely look at the boxes. Do we have overlap? Here we have the medians. We don't do tests for the medians in this class, but often these are good indicators of roughly where the center is. Are they close to each other? Are they far apart? These are all things we absolutely are going to look at. So you can even look here. The spread for server B is a lot larger than the spread for server A. There's a number of things we can look at. You can see like, hey, is it roughly symmetric? Although a box plot alone can't really tell you. You're probably going to need a histogram. But definitely side-by-side box plots, they're useful for just kind of a quick glance. How did these two groups compare to one another? So when we want to do two sample T confidence intervals, this is when we want to estimate the difference between mean of population 1 and mean of population 2. Absolutely, you're welcome to use different subscripts than 1 and 2. If you do use subscripts 1 and 2, you should say what subscript 1 is and subscript 2 is, just to make it very clear which direction you're subtracting in. So our conditions for inference, the first one is going to look similar. In fact, it should look similar no matter what procedures we're using. So samples are random and representative of the population. This is something we always do want. And then based on central limit theorem, the sample size for population 1 and the sample size from population 2, they're both big enough that we could count on the sampling distribution of x bar 1 to be roughly normal and the sampling distribution of x bar 2 to be roughly normal. So we need both of our sample sizes to be big enough. If you have a small sample size and it's really, it looks really skewed, that might be a problem. And then here, and that's really what's going to distinguish this lesson from the next one, is we have two populations and they're independent from one another. And part of what that means is an observation in one population can't also be observed in the other population. They can only be observed in one population at a time. So it could be something like, hey, I'm looking at high school seniors in Corvallis versus Albany. You're not going to, hopefully, I don't know, have high school seniors enrolled at both, right? They would be independent groups, that kind of idea. So the structure for our confidence interval, when we want to estimate the difference between the means of the two populations, so we are trying to estimate, our parameter of interest is mu1 minus mu2. Absolutely, feel free to subtract in the order that you want. However, you need to be consistent and keep tabs. Like, it must be absolutely kept track of. Okay, don't mind that. That's my cat running after her food. So if I want to estimate the mean of population 1 minus the mean of population 2, my starting point, or my point estimate, is going to be x bar 1, so my sample mean for the sample from the first population, minus x bar 2. So then times t star, so I will have to specify my degrees of freedom, and I will have to specify what confidence level I'm looking at. That's what the alpha over 2 is about. And then now the standard error for x bar 1 minus x bar 2. It's a little more complicated than we were doing before. So it's going to be the sample standard deviation from the first sample from the first population squared over n1 plus s2 squared over n2. So we will need to specify our degrees of freedom, and we'll talk about that there. And yeah, this is a Welch's T procedure, which is an unpooled test. So what that means is, in this scenario, we are not assuming, we don't assume that the standard deviation of the first population is equal to the standard deviation of the second population. We do not want to assume that by default. It is called a pooled procedure when you do assume that that's true. So Satterthwaite, I'm sure I mispronounce it every time. I'm going to go Satterthwaite, even though the H is not in the right spot. So if you were to run this through R or a calculator, you might notice you get some real goofy looking degrees of freedom for this. So nu, this is a Greek letter nu. These are our degrees of freedom, and it's this delightful, messy equation. Absolutely, you're welcome to calculate this by hand. If you look in the R code provided for this week, we did provide R code that you tell it what S1 is, you tell it what N1 is, and it will give you the Satterthwaite degrees of freedom. Note that a lot of times when you calculate these degrees of freedom, it will give you some sort of decimal or fractional number. It won't necessarily give you an integer, in which case you'd want to round down to the nearest integer if you're going to use the t-table. If you're using R, R can handle it. It doesn't need to round to an integer. However, if you are using the t-table, round down to the nearest integer if you calculate your degrees of freedom this way. What we're going to do most of the time, because this is disgusting and doing this calculation by hand is really, really gross, we're going to use our conservative degrees of freedom. So what you're going to do is you're going to take the smallest sample size. So you have two samples, sample 1 from population 1 and sample 2 from population 2. Take the smallest one and subtract 1. And those will be our conservative degrees of freedom. In this way, we don't have to worry about rounding or any of that. So most of the time, I'm going to roll with this one. It's more conservative. Typically, the degrees of freedom here will be smaller than the Satterthwaite degrees of freedom. So 2 sample T confidence interval. Back to our example here. We're looking at server times for server A and server B. In particular, we're going to end up wanting to know if server A is faster. But right here, we want to have a 95% confidence interval for, I did mu A as the mean server processing time for server A, and mu B as the mean processing time for server B. So here, they went ahead, they took a random sample of 30 and recorded the processing times for all of them. We have a sample mean for each server here, and we have a standard deviation for each server. So my question of interest, where I want to start, is, and I like to, so since I picked here, I'm going to go with server A minus server B. So what is the difference in the mean processing time for server A and the mean processing time for server B? I can't end the sentence yet. I have to specify server A minus server B. Super important. I really can't emphasize enough. we will absolutely be making sure that this is written in a way we can tell which direction you're subtracting. Because if you don't really make this clear, it makes it very difficult to do the write-up. So my parameter of interest, it's right here. So in notation, it's mu A minus mu B. So the mean processing time, and all this is in seconds, for server A, the mean processing time for server B. So one thing I want to be very, very cautionary, mean difference, not here. Next lesson, yes. If you have matched pairs, yes. But do not ever call it a mean difference if you mean a difference in means. If there's more than one mean, it needs to be a difference in means. Mean difference is for matched pairs. So then to inventory here, we're going to go ahead and I'm going to use the label A to indicate server A. So I'm just pulling these from this table right here. So seconds, SA is equal to 0.5 seconds, and NA is equal to, I love it when, I really can't emphasize enough, when the sample size is the same for both groups, it makes things so much easier. So this is all server A. And then I'm going to write the same information though, but for server B. So 7.3 seconds was the average processing time for server B. The standard deviation for server B was 1.3 seconds. It's a bit bigger than the other one. And my sample size was the same, it was 30. Server B. So that is what we are interested in looking at there. So once again, I like to check my conditions before I start doing a lot of work. Absolutely, you can go ahead and figure out your T critical value, but I'm going to just check the conditions real quick. So do our data come from random representative samples? There's more than one of them. So yes, so we went ahead, we had 30 times on both of these from the prompt. We are supposed to believe that, yes, these were random samples of computer algorithms that were being executed. So we're going with yes, this represents all the computer algorithms being processed by the two servers. Over what time period? I'm not sure, but that's worth noting. Then we want to know, hey, are our sample sizes N1 and N2 large enough? So I'm going to call them NA and NB. NA and NB are equal to each other. We have 30 in each group. So while we don't know, well, we do have box plots. We could absolutely look at histograms, look to see if they're roughly normal. If the data in the sample, each sample is roughly normal, you could probably assume that the population is roughly normal. You can't tell the shape alone from a box plot. You're going to probably need a histogram. However, because we have 30 in each group, we're going to say, you know what, no, we can probably trust that the central limit theorem is going to kick in. It's probably going to be okay. So yes, we did meet the size requirement here. And then other populations independent. Yes, so the computer executions didn't go through one and then the other. They were running on their own servers. They're independent. So there you go. Yes. So now step 3. So my confidence level, just double checking here. I am doing a 95% confidence interval. My degrees of freedom. So smallest, I'm going to even write I'm going to do the conservative degrees of freedom. So NA, NB. Hey, look, this is one of those really handy things when the sample sizes are the same. The minimum of 30 and 30 is 30. So 30 minus 1 is going to be 29. So I'm going to use the 29 row. I'm going to use the 95% confidence column where it lines up. I'm going to use T star equal to 2.045. So I don't want to use the Z star because I can't use Z methods here, but I can use T methods, which means I need a T critical value. Absolutely feel free to calculate the Satterthwaite one, but it's not going to be this. It's about 37.4. If you're using the T-table, you're going to actually notice that it jumps from 30 to 40. In general, you don't ever want to round up. You always want to round down. It's almost like taking credit for a sample size. You do have degrees of freedom of at least 30. You don't have degrees of freedom of at least 40. So 30 would be more conservative. Use 30. So either way, we're going to use the 29 or the 30 row. We won't be too particular, but you have to make it clear. Like, you're using the 30 row because you're using the Satterthwaite degrees of freedom versus using the conservative degrees of freedom. It does need to be clear there. And in general, just so you know, we're not going to sit there, definitely not any sort of quiz or exam, ask you to calculate the Satterthwaite degrees of freedom. We almost always will just stick with conservative. It's much, much easier to calculate. So calculate the 95% confidence interval. I'm going to write my information in here again. It helps me stay organized. So 7.3 seconds. I have 2.045, 0.5, 1.3, 30. So now I have all the information I need to plug into here. So if I wanted to have my 95% confidence for interval for mu A minus mu B, I'm going to start with the difference in means that I saw in the samples. That's my point estimate. So 6.5 minus 7.3 plus or minus, so my T star, 2.045 times 0.5 squared divided by 30. And this is part of why I say I absolutely love it when the sample sizes are the same, because if you are doing this like with a calculator or it makes it so much easier to do that addition. Absolutely, it's not the biggest deal there, so I'm going to end up getting -0.8 because it's a smaller number minus a larger number, plus or minus 0.52. No, I did round here. It went to more decimals there. So I end up getting -1.32 seconds to -0.28 seconds. So things to note. It now is when it's really important to remember what order we did subtracting in. I did server A time minus server B time. So if I'm getting a negative value here, that means that the average server time for server A was shorter. The average server time for server A was smaller than it was for server B. So server A is faster. That's what this is implying. And I'm going to use that information. I'm going to use the order I subtracted in to help me do my write-up. So my interval here for mu A minus mu B, just going to write that there, minus 0.28 seconds. So looking here, the 95% confidence interval, and I'm going to put the mean for server A first, and then I'm going to estimate it's this to this much faster than the mean for server B. So the mean execution time of server A, so this is for all computer algorithms, is on average estimated to be between, so here it's not just that you want to put the values and the units, you're going to want to put higher or lower depending on if it's a negative, so or faster here. So between, I'm going to put 0.28 seconds faster to 1.32 seconds faster. Oops. With a point estimate, so now I want to think about how fast it was, how much faster it was in the samples, of 0.8 seconds faster than the mean execution time of server B. So I do need to put the mean of server B in there. So the 95% confidence interval for the mean execution time of server A is on average estimated to be between 0.28 seconds faster and 1.32 seconds faster, with a point estimate of 0.8 seconds faster than the mean execution time of server B. So me sticking to this particular order, a big reason is if I had minus 5 seconds to positive 0.7 seconds, this is a lot harder to interpret if you just talk about the mean difference. So I could say, hey, the mean execution time of server A is estimated to be between 0.5 seconds faster to 0.7 seconds slower than the mean server time of server B. That's why I'm sticking to this slightly funky format. It's a lot easier to do than to just talk about the mean difference and say which order, because when you talk about differences that are negative versus positive, it's a lot more confusing to read. So now that we've done the confidence interval, we might be interested in doing the test. We might want to know, hey, is there a difference in these? Or hey, is the average time for this server faster? Because if you determine that it is, it might be worth paying the extra bucks per month, you know? So here we want to test the difference between the averages. So you have the mean from one population group minus the mean of a second population group. Our conditions are going to be identical as they were with the confidence interval. We need representative samples, so usually we're going to go with random samples here. We need to know the central limit theorem is going to kick in, so we need our sample sizes to be big enough. So if we are looking at histograms of the sample data, they either look approximately normal and or we have big enough sample sizes, at least 30. In general, if you have sample sizes of at least 30, you're good. This is going to meet that condition. And then for a 2-sample t-test, the 2-sample part, you're going to need the populations to be independent. So here, our hypotheses, they're going to look a tiny bit different. So you might notice we've got delta here, delta naught. This is a claimed difference. The vast majority of the time, this claimed difference is going to be 0, right? Because if there's no difference between the two groups, the difference between the means would be 0. Almost always this is going to be 0. Not always, but most of the time. So the null starts out assuming nothing interesting is going on. The means between the two groups are the same. if you're doing lower one-sided, you would say, oh, well, actually, I think the average of, you could even translate, like, I think that the average of population 1 is lower than the average of population 2, that kind of idea. And absolutely, you can do one-sided the other way. You can do two-sided. So our test statistic is still going to be a t-test statistic, which means we're going to reference a t-distribution when we want to find our p-value. So we calculate a t-test statistic by taking what we observed in the samples, so the difference in means in the samples, minus the claimed difference, this is almost always 0, over this standard error. And then we're going to go ahead, our reference distribution that we'll use, it's going to be a t-distribution with new degrees of freedom. If you're using software, you can go ahead, like it'll automatically do the Satterthwaite one's degrees of freedom for you, or you could even use the conservative degrees of freedom so that you take the smallest sample size minus 1. So back to our computer server problem. Server A supposedly is faster than server B, but it is more expensive to have an account with server A, so they decide, hey, if there's evidence that server A is faster than server B, they're going to consider it worth it. They're going to go ahead and pay the extra and get server A. So here, what is the question? Note anytime that we have hypothesis test, I know it's going to sound like a broken record, it's going to be in the form of a yes or no question. So, is the mean execution speed of server A, mean execution speed of server A, so for all executions, if you're including your population, is it shorter than? So is it shorter or faster than the mean execution speed of server B? So once again, for all executions. So definitely the sentence is getting a little bit longer now that we have two populations. But we want to know, hey, you need to mention that there's a mean for both groups, right? So you could say, is the difference in means different than 0? But you have to be very specific and specify what direction you're subtracting in. So like you need to put in parentheses, server A minus server B, that kind of idea. So my parameter is going to be the same as my confidence interval, mu A minus mu B. So this is my parameter in notation. And then if I want to write it in words and context of the problem, it's going to be the difference in mean speed to execute all computer algorithms between server A and server B. So specifically server A minus server B. I need to be very clear about which direction. If you say difference, you need to tell us what direction you're subtracting in. So then inventory, this is going to look very, very similar to before. So you'll have X bar A, SA, NA, so 6.5 seconds, 0.5 seconds, 30, X bar, B, SB, NB. So this is probably the uninteresting part where I'm sitting here just writing, and then because it is a hypothesis test, the null difference. So if nothing interesting is going on, there's going to be no difference between the two means. So the mean execution time of server A and B. So 0 seconds is going to be our default or our claimed difference. Significance level is going to be alpha is equal to, is it 0.05? In general, if you do a 95% confidence interval, your hypothesis test will be 0.05. That is generally what we will do most of the time. If you add the significance level and the confidence level together, it would equal 1 or 100%. So state the null hypothesis and the alternative. So here, this is my parameter of interest. You always have an equal sign in your null hypothesis, and then 0 seconds. So this implies that the average time, so implies average process time is the same. You might also see mu A is equal to mu B. All I did was just add mu B to both sides. In part, we tend to prefer the format in this first one because it makes it really obvious what the null difference is. It's not always as obvious if you put it in the second format what that null difference will be, especially in the weird cases where the null difference is not 0. So here, mu A minus mu B, and we're still going to have 0 seconds. So here, we want to imply that UA is faster or smaller than mu B. So if that's true, I'm going to have less than. So if I have a smaller average time minus a larger average time, I should get a negative number. So this is going to be a one-sided lower tail test. So what that means is when I go ahead and I calculate my t-test statistic, I'm going to want the area in the lower tail, and that will be my one-sided p-value, and I'll want a one-sided p-value. So my conditions, I stuck them after only because we already checked them. Do our data come from representative samples, just as much as they did before there? Our sample sizes here, they're both 30. 30 is kind of like that magical number where we tend to think, oh yeah, okay, good, they're big enough. If they were both 29, unless we had real skewedness going on in the data in the two individual samples, I probably wouldn't be too worried. Are they independent? Yes, they're just as independent as they were before. So going ahead, calculating not the confidence interval. Whoops. It's one of those hazards of copy and paste, right? The test statistic. Not only that, it's the t-test statistic because I meet the conditions for the t-test. So condition for t-test statistic. So 6.5 seconds, 7.3 seconds, 0.5, 1.3, 30 degrees of freedom. I'm going to go with the conservative degrees of freedom, and I'm going to write that I wrote conservative. In part, it's really easy to take the min of 30 and 30 and then subtract 1. And then my claimed difference is going to be 0. Remember, the null is nothing interesting is happening, not what you suspect or you're interested in finding. It's the thing that would not be interesting. So here, I'm going to go ahead and take what I found in my sample, so 6.5, whoa, minus 7.3. I'm going to subtract 0. I love subtracting 0. It just cleans right up. So 0.5 squared divided by 30 plus 1.3 squared divided by 30, square root all of that. So as you can see on top, that 6.5 minus 7.3, right off the bat, that's going to give me a negative value. So I know that my test statistic is going to be a negative value. So a little bit of rounding, I get it's about negative 3.15. So here, I'm going to throw here, negative 3.15. Remember, it's a lower one-sided test. But you might notice the t-table only gives us the upper tail. So we're going to use the information that the t-distribution is perfectly symmetric. So the idea is if I want probability t29 is less than negative 3.15, that's the same as the probability that t29 is greater than positive 3.15. So if I look at the positive end, these two areas would be the same. So I'm going to go with this over here. So my degrees of freedom, I'm using the conservative. Absolutely, if you wanted to go with Satterthwaite, you could use the 30 row. It's not going to make a huge difference. So my degrees of freedom are 29. So now what I'm going to do is I'm going to look in this row, for as close to 3.15 as I can get. So, for example, if I look between these two, 3.15 is not between those two numbers. It's not between these two numbers. So I'm going to keep looking to see where 3.15 would be on the row. Keep in mind, it could run off the edge. It doesn't here, though. I have 3.03, it's smaller, there we go. So my test statistic is somewhere between these two numbers. So what I'm going to do is I'm going to go up and go, hey, my one-sided p-value is between those two numbers. Be very careful about the order. You don't want to say it's between 0.0025 and 0.001. That's not the right order. So my one-sided p-value is between 0.01 and 0.0025. So it's somewhere between these two numbers. If you are using a t-table, a range of values for the p-value like this is perfectly acceptable. Quite honestly, you could even tell us your one-side p-value is less than 0.0025. Because knowing that it's less than 0.0025, my p-value is going to be less than that 0.05. So I know that I'll reject. Once again though, if you have R or you have a calculator like a TI-84 or 389, I don't know, they have a ton of numbers, and you feel like you're comfortable plugging it in there, you can get a more exact p-value. You can get an actual decimal number there. Keep in mind, if this was a two-sided test, I would multiply everything here by 2. So I'd have 0.002, two-sided p-value, 0.005. However, this is a one-sided test, I'm not going to multiply by 2. So here, with a p-value, I'm going to say between 0.001 and 0.0025 at the 0.05 significance level. So we said, hey, that's a small p-value. We're going to reject the null. And then I am going to mention, hey, this was a one-sided test, the t statistic was minus 3.15. Our degrees of freedom, we used here 29 at the 0.05 significance level. Oops. Note from my p-value, I got something like 0.0012. So it is between 0.001 and 0.0025. So I am happy. But just know that either one is perfectly acceptable. This exact value or this range of values that's accurate and precise. You don't want to say, hey, it's between 0 and 1. We're going to say, yeah, duh. So remember to be specific enough. So here, this is a pretty small p-value. In general, if it's smaller than 0.01, we think, hey, this is really strong evidence that the null is not true and the alternative is. So we're going to say, hey, we have convincing or very strong. You don't have to write both. Just writing one is fine. So convincing or very strong evidence to suggest that the mean execution time of server A is faster than the mean execution time of server B. So pay the extra. So things to note to get server A. The hypothesis test tends to kind of answer it in a yes-no sort of format. Hey, is it faster? And you say yes. The confidence interval would be useful as a follow-up here because then we could say, well, up to how much faster? Because in the confidence interval, we determine that on average, it's estimated that with 95% confidence, server A is about 0.28 seconds faster to 1. Oh my gosh, I forget the other part. 1 point whatever seconds faster, which might be enough information for them to say, okay, it's faster, but is it fast enough? And this is getting at the statistically significant difference versus practically, because yes, it's faster, but maybe it's not enough faster to make enough of a difference to pay. So keep in mind, a lot of times we'll use these two together because the one will tell us, hey, yes, there's a difference, and the other will tell us, hey, well, what do we estimate this difference is? And that difference may not be enough to motivate them to pay the extra bucks. So then we have a caution here about pooled T procedures. So the procedure we just did is called an unpooled T procedure because it does not assume that the variances are equal for the two populations. So we had two independent populations, and we went ahead and used S1 and S2 from each sample. We generally don't like to assume, though, that the variances for the two are equal. So, for example, we have two populations below, population 1, population 2. We have simulated these so they have the same mean. So mu1 is equal to mu2 is equal to 50, so you can see they're both centered at 50. However, the standard deviation of the first population is not equal to the standard deviation of the second. If you see, this one is so much more spread out. These are obviously not on the same scale, right? This kind of goes like you see from about 46 to 54. Here you see from like 20 to 80. It is so much wider, right? It's really deceptive because of the scale here. However, you would think that if you know that the means are equal of the populations, that means that you should, always fail to reject. However, you really do increase your type 1 error. You reject more than you should here. So instead of rejecting at 5%, if you're you're going to end up rejecting at 6.3%. It's going to increase your type 1 error. People are very upset about this. So in general, it's better to use Welch's t-test, which does not require the extra variance assumption. I'm going to write on this next one. So unpooled does not assume, it does not assume this, and this is always okay. Pooled, well, I'm going to write here, pooled assumes that the two variances are equal, and it's only, your results are only really going to be okay when this is true. So it's only okay sometimes. The unpooled, you're going to essentially get to the same place as the pooled when the two variances are equal. And the unpooled is going to be a lot more reliable when they aren't equal, so just stick with the unpooled. And there is an option in the t-test function where you can tell it to do the pooled versus unpooled. If you just leave it as is, the default's going to be to do unpooled, so that's where we are. So just know there is that other option. You might hear about pooled tests. Most of the time, it's really not going to be worth it. You really need to demonstrate that you can reliably say, like, yes, these two populations have the same variability, which often is not going to be true. So that's going to be lesson 28. We'll go on to lesson 29 when we're going to talk matched pairs. So lesson 28, we talked about two independent populations or groups. Now we're going to talk specifically when we have matching or pairing. So we'll see you there.